Hello, I'm Jack Rickard with EVTV. This is my compadre and consigliere. Actually, he's not here this week. Brain is going to California to visit his parents. I believe his father is having open heart surgery, in fact. But he's going to visit a few of our supporters out there this week, try to drum up a little business. So I'm here in the shop by myself. This could be a short, but at least boring show without the brain. I'm revisiting the Vantage Green van here. I'm calling it the daughter van. You'll recall a year or two ago we bought this on eBay for $4,000 and removed 750 pounds of AGM cells from it. Put in 27 high-power 200 amp hour cells. We had a young intern with us at the time named Matt Hauber, who's now in San Diego. He and a partner have a conversion shop out there. But this was where he mixed two piles of high power cells together, one that were all pretty much the same and one that we had been using in the shop. And so he got to do a lesson in bottom balancing the hard way. And he did a really good job on it. It took him several days, these big 200 amp hour cells, but he replaced the 750 amp AGMs with about 750 pounds of AGMs with about 350 pounds of these lithium iron phosphate cells. Wound up going from a 16-mile range to a 100-mile range. The front tires on the vehicle, because of the weight, this was just pretty badly engineered little van conversion because of the weight. The inside edge of the tires with 650 miles on it were completely bald, and the outside edge still had the fur on it. We've since had to replace the tires. These little vans, when I was stationed on the USS Midway in the early 70s, we were home ported in Yokosuka, Japan. And they had all kinds of these little vans about this size. Nissan had them, Toyota had them, Datsun had them. And I thought, sure, as they hit the States, they will take over everything. For some reason, unbeknownst to me, but probably known to American automobile makers and the National Highway Traffic Safety Administration, in some sort of collusion, the Japanese vans were kept out of the States. And I think they would have just taken the whole country by storm if they'd arrived. Vantage Green van has imported a Chinese version, and it's not the same as the Japanese. We've already battled one of the window rollers, some of the door things, some corrosion underneath. This is not the finest built van in the world. It's kind of cheap Chinese. However, I still like the form. It has all these doors, kind of a low floor, and it's easy to get in and out of, and it's small. And with our 350 pounds of lithium cells, it does quite well. I've let my daughter use it since Matt had departed, and she's using it to go to school. We never did build in a daughter mode, and so she's actually run the batteries completely out twice, predictably enough. However, because of Matt's excellent bottom balancing, it does not appear to have harmed them any. We still seem to have full capacity. She brought the van in saying it was behaving terribly, jerking and jumping, and I confirmed that. And my worst fears, of course, were that the battery pack had been destroyed. Imagine my surprise when I found out that the batteries were all pretty much at the identical voltage and mostly fully charged. And so we went to looking at some other things. Brian reports that actually right now, our friends at HP EVS that do the little AC50 with a Curtis controller are doing some work on a lithium version of this van. These guys were selling these with lead acid, but they're doing some work on it now. We're kind of a little ahead of the game with these high powers, and but it does have a Curtis controller in it. I'm not sure the exact model number, but it's about an 84 volt controller, and it has some VCL in it that has some limitations, like on the speed of the vehicle and so forth, that I haven't been able to change. This is the Curtis 1311 controller programmer. Now, you don't actually program it. This is a thing that will read the configurable variables out of the controller into memory in here. You can change them, and those changes are reflected in the controller. And in fact, you can take that set of them and take them to another vehicle and plug it in and save those off. And so copy one vehicle to the next. I normally like a little laptop thing, but this has been so handy, and we use it so much that I can recommend it. They're about $500. So I pulled it out and checked the faults on this, and it had quite a history. I cleared the history, ran it a little bit, and I kept getting a over voltage cutoff fault. Let's talk about that a little bit. It's fairly unusual, but it's related to the most common mistake. And since I fixed another car this week, a guy had a Porsche, I think a 911, that just was, he had this Soliton set for about a 140 volt cutoff on the low voltage cutoff, and wanted to know if he could drop it to 130, and that the car really wasn't doing quite as well as he had hoped, although it was running okay. And this is the most common mistake made in configuring a controller. I've made it. I've even made it multiple times. I've even made it multiple times after knowing that it's the most common mistake made. So watch out for this one. If there is a low voltage cutoff in your controller, and they always seem to provide this, as useless as it is, this is meant to protect your battery pack, where when it falls to a certain voltage, the controller kicks out. But it doesn't really kick out, it cuts back current to prevent taking the batteries below a certain voltage. What happens if your batteries will naturally, as a function of their internal resistance, decrease in voltage as they deliver current, and to a much larger degree than most people doing a conversion would imagine. The large-scale prismatics that we get from China, this is typically between 20 and 25% of the total voltage. And so a 100 volt pack, it's not unusual to see that diminished to 80 or even 75 volts when drawing a lot of current from it. Similarly, a 200 volt pack would go down to as low as 150 volts. So this is not an unusual case. This guy had a 170 volt pack, and the low voltage cutoff was set for 140 volts. In that event, when it reaches 140 volts, the controller reduces the current draw. And when it does so, that increases the voltage, because we're having less drop across the equivalent series resistance in the batteries. And so as the voltage comes up, the controller can then relax this current cutback. Well, that will then increase the load on the batteries, and the voltage will go down. Now, this happens, 8,000 or perhaps 14,000 times a second. And so what you have is a very smooth, you'll depress the accelerator pedal, the current load on the battery will come into play until you reach your low voltage cutoff, in this case 140 volts, and then it will simply sit there. And any attempt to take more current will result in the voltage lowering and the current cutback, and any attempt to take less. And so it feels like you have the thing floored, it's working perfectly, and it's just not a very exciting ride. Actually, it's a simple configuration, and in this case, I told the guy I would take it down to 70 volts, not down to 130 volts. It's not going to do anything for you, and it can only hurt. He reported back the next day, wow, is this fun? and that's usually the reaction. It's, I'm a little disappointed in my electric car, to, wow, is this ever fun? And that's the difference that low voltage cutoff can make. High voltage cutoff's a little different, but not a whole lot. We don't want to put any more voltage in the batteries than they can take. And of course, with the AC or SEPX type situation, we do have regenerative braking. And so often they will also include a high voltage cutoff. Well, of course, we have a little bit different voltage situation here than we had. I don't know if we have a bad connection. I'm still checking, but immediately I went in and raised the high voltage cutoff, and it quit. And so I expect I've got a little bit of a connection problem to the battery pack, probably through the contactor. That's all underneath the vehicle, subject to corrosion, and I'm probably going to take off some of those connections and clean them up a little bit. I can see blue corrosion on them and so forth already. It was operating without complaint. Now it has a problem. That's probably a sign of a bad connection. I need to keep looking. We'll find it. Meanwhile, the problem has kind of gone away. We do have another problem with the vehicle. My daughter reports that it is quite cold to drive. This makes perfect sense. It's not insulated, has no heater, and it is January here. Actually, it does have a little heater that you put a little bit of diesel in, and it's some sort of thing that fires up under the dash. I'm terrified of it. It's tiny, it's right in front of your face, and it burns diesel fuel. And I wouldn't put a drop in there. So we need to make her a heater. We have visited this issue in the past, but I thought a little review might be in order. This is a ceramic heating element as found in many Walmart $15 heaters, typically 1,500 watts. That seems to be as much as they will allow. And it has a ceramic elements. This has 5 tabs across the top. That gets everybody excited. Picture the one in the middle and the one on the 2 sides as being one leg. It can either be your positive or your negative. There is no polarity to these. And the other 2 tabs that are in between as being the other leg, again, positive or negative. We typically put our negative or black wires on the 3 that are the 2 outside in the center, and our red ones on the 2 on the inside. And you can use, these are the size of a normal automotive spade terminal. And the interesting thing about these, and why I like them, is they're called positive temperature coefficient ceramic heaters. And that is that you can apply current to them, but as they go up in temperature, they will also increase in resistance. So there's a positive relationship between resistance and heat on these. And so as they get hotter, the resistance goes up. When the resistance goes up, the current at any particular voltage will force through it, and so the power is reduced. And so it's kind of a self-regulating heater. It's also kind of interesting in that it varies how much power it'll put out based on the airflow that passes over it. And so many EV conversion people will take one of these, take their heater core out of their car, and kind of gut it and mount one of these in the middle, put it back in the car. They can then use their normal blowers and doors, valve doors, and so forth in their car and have heat with no water system at all. I usually prefer to retain the water system, and so we don't do this a lot in cars, but the little VW cars that don't have a hot water system, we do use this. And in this case, we have no hot water system and really no heat other than a diesel heater. And so we're just going to make one in the cabin to fit on here. Let's take a look.
Net Gain Motors, home of the Warp, Trans-Warp, and Impulse motors, introduced the improved Warp 9 motor. The Warp 9 is a 9 1/4 diameter series wound DC motor with a double-ended shaft featuring 26 improvements for 2010. Externally, the terminal studs have been enlarged from 3/8 to 1/2 inch diameter. Bigger is better. On the inside, a larger commutator, new brush composition, and split brush design with heavier springs handle even higher voltages and currents than before. Our new fan increases airflow by almost 50% over typical paddle-style fans. And all this translates into improved performance. For even more performance or larger applications, take a look at Net Gain's Warp 11 motor, an 11 3/4 diameter series wound DC motor for even greater torque and power. Since 2002, Net Gain Motors has been leading the EV industry with precision, performance, and price. Visit us at go-ev.com. Net Gain Motors, warp power to go.
This van is kind of a big square box. It has quite a bit of cubic area in it, no insulation. But this is a little steel cover that we already have that covers our batteries behind the seats. What we've done is taken a little dual fan squirrel cage thing here and mounted it with a piece of aluminum to that steel where it kind of floats there. And we've taken two of these PTC heaters and put them, screwed them to the front of it, which fit pretty easily and nicely. That worked out pretty well. This is not the heater, but here they are, and you can see the wiring. I have run all the black wires. I used to try to jumper these and go from one to the next. It just doesn't work very well. It's easier to run one, and these are 10 gauge wires. You want a fairly heavy wire. These are going to be 1500 watts. We have about 90 volts, and so you're talking about 15 amps per side here from your battery pack. Because these are 120 to 168 volt elements, it won't draw quite that much. It'll be about 20 amps total between the two of them, but I still like to use fairly heavy wire in the heavy terminals. And you can see I've got 3 black, the center one and the 2 sides, and then 2 orange. The 2 orange ones go to a kilowatt contactor that I have mounted to the steel thing here on the back. And it simply goes to one of the terminals, and the other terminal will be my positive pack voltage. And so I've got 2 wires here wired up, one for negative and one for positive pack voltage, and that is what will run our heating elements. Now the fan is a 3-speed fan, and so of course it has a 3 wires. I've hooked up a fuse line here to a little 12 volt battery and a 3-position switch. And the way I've got this wired is the contactor is wired to the highest speed. Now this is a little counterintuitive, but the coils in the different windings in the motor for the different speeds are kind of wired together anyway. And so an interesting thing happens in this case. If I can get 12 volt power to it through a fuse, of course, I turn it on low and nothing happens. Here's my ground. I'm using the steel thing as a ground. I get a little whir here, but my contactor does not close. If I go to medium, I get enough voltage through the coils of the fan to energize the contactor and turn on the heaters. And of course on high, I'm actually tied with a contactor to the high terminal, and so it'll do it. So this actually puts out quite a gale on high. As I turn it down, there's medium, I still have heat. When I turn it to low, the contactor remains engaged. And that's because it takes a lot more current to engage the contactor, about at 1.3 amps, than it does to maintain the contactor, which is a couple hundred milliamps. And so when we start up, you can't really start at low. If you do, you're just turning on a fan and moving around a little air in the compartment. Not a bad idea, actually. If you go all the way to high, you're turning on the heat and you're blowing full force, but as you get warmer, you can turn it down and the heat stays on. Now, not only does you have less airflow through the heating elements on a lower speed, but actually, because of this positive temperature coefficient, you'll actually be using less current. You'll be able to measure less current actually from the battery pack into the heating elements while you're doing this. So this is it has one motor and two squirrel cages, so I put two of these heating elements. If I wanted more, I could stack them and have it blow through two on each side, but I think this would be more than adequate to heat that little van. Again, we use a high voltage relay, or high current relay, Tyco Kilovac ANA. Just this is the same contactor we use on a lot of the vehicles to apply voltage to the controller. And that may seem like overkill, but this is an important relay in that we do want it to open when we remove power. And I've had some problem with relays here if they have very much current at all with the marking and the contact sticking. And we had tried some other relays on heaters and found incidents where we turned them off, but they stayed on. And the fan's off, but we still have power to the heating element, and it won't cause a fire hazard really because it's a positive temperature coefficient. It gets to a certain level and it won't go beyond that. However, it will drain our pack completely flat, and we don't really have an indication that this is going on. It's quite silent in doing this, and so this is a little bit dangerous. So we use a $65 totally overkill contactor, a high current relay, to switch power to our heater, and we always will at this point. And I would recommend you do the same. It's a little enough to spend to keep it going. So this will put out good heat. It'll blow it kind of forward toward the seats, and so it's not a perfect thing. It's sort of a quick fix to get a little bit of heat in that van for those January days. You can get in and flip that on. We're going to, of course, make a hood over this thing and some aluminum screen that I have for the intakes and the outflow, and just put a aluminum hood over the top of it to shield this from prying hands and so forth, the children, and put a switch on it. Well, this is the switch. Here's our 3-position switch. We'll mount that, and it should be good to go. So that's what we're doing with the Vantage Green van, is we're adding a little heat. We checked the batteries quite carefully. They're great. In fact, they're in great shape. And we have cured the problem with the controller change, but we're going to spend a little more time looking for corroded connections underneath the vehicle around the contactor and controller to make sure we don't have a bit of a voltage drop there that we don't know about. And that should get us back on the road and get the daughter back in the Vantage Green van. This episode of EVTV is brought to you by the Winston Battery Company Limited, makers of high-capacity lithium-yttrium rare earth cells, including the popular 160 amp-hour model featuring cycle lives in excess of 5,000 cycles when discharged to 70%, the longest useful working life of any available battery of any chemistry. A leading battery technology scientist, inventor, and entrepreneur since 1995, Mr. Winston Chung envisions a new world of clean electric power for the dawn of a new era of electric vehicles. For your next electric vehicle design project, contact Winston Battery Limited. Energy for a bright future. I had mentioned that our module number 2, our 40-volt module, had failed. It's a somewhat catastrophic failure. It blew off the resin off the side. Here's one of our little heat wicks. That's going to be a quick way to get me cut, I believe. If I'll work at that a little bit. There is our heat wick. And as you can see, our pouch has expanded dramatically. We actually did lose electrolyte on this adventure, and you can see here it split our pack completely lengthwise over here. What happened? You know, I'm not sure I'll ever know. We suspect the exothermic reaction of that resin pour. These cells were done 4P and 12S serial for 40 volts and 80 amp hours. And I tested this pack once it was assembled to 77.5 amp hours. It was actually very good, I thought, for a 4-cell pack. This is the resin. It's quite hard yet, a little bit flexible, but quite hard for something that thin. And this just split it wide open in a couple of places, down here and here. And it did it by a very strong pack swelling process, and the escape that you could detect by smell very easily of electrolyte, which also ran out on the ground. I mean, it was not, there wasn't any question about this. And this, my golly, it's going to come apart for us. Really did bust lengthwise and really made a mess. And this was 48 cells, probably $1,400 worth of materials. What happened was I had 75.75 amp hours on it. I cast it in resin, drained it, and somehow got about 65 amp hours out of it, and it was quite low, down around 2 volts per cell, 24 volts. So then I charged it back up about 65 amp hours, and it blew up. And so clearly the capacity of some of these cells was diminished. And I'm not sure why that was so. I did have to put the aluminum between the cells, and I might have scarred them somehow that way. I don't see signs of that. And then, of course, we have the resin locking it in. They shouldn't normally swell, but this one's swollen, this one's swollen, this one's swollen, so a number of them had decreased in capacity. And I would guess at this point that the 170 degrees exothermic heat of the resin curing process is messing up some of the electrolyte in the cells, reducing their capacity. And had I limited that to a 60 amp hour discharge and put 60 amp hours back in, it might still be okay, but it would not be the pack that we wanted. And if that's going to be the case, we don't want to do that much more. Let's see if I can get it entirely separated. There's probably another piece of nylon down here. No, they're both broken. It's just a matter of prying it apart, I think. One of my thin aluminum sheets. For heat. So there you go. These pouches are swollen. And we're getting some marking yet from in them. They still have some active material in there. Again, these things don't usually leave much in the way of visual clues, except they are swollen, and they this is kind of interesting. Here's the inside of the pouch. Polyethylene separator. Not so much different from an ordinary cell. Copper separator. Here's your copper anode. Carbon. Separator. And here is your cathode material, which on the A123 is a nanophosphate on aluminum foil. Now this is kind of interesting. It goes to the heart of a patent dispute. The professor at MIT who's claiming these cells don't have anything to do with the Fostech patent, Hydro-Quebec, and the University of Texas at Austin. Professor John Bernard Goodenough and his team there had purportedly set up the lithium iron phosphate cell. One of the issues that they had in doing that was that lithium iron phosphate actually does not conduct. Now, it conducts ions just fine. They can tunnel into this porous lattice and intercalate with the iron phosphate just fine. But electrons can't from the anode or the cathode material, the aluminum, cannot penetrate the iron phosphate. Now, how do you get that to support electron current flow as a result of the ions? The standard way to do that is to dope it with a little bit of carbon. And the carbon, of course, supports current flow. But this material is much shinier and slicker than that used on the Chinese batteries that we get. So they've had a difficult time in this patent war in collecting from A123. A123 claims they did not use carbon, that they used another rare earth metal like, it could be vanadium, could be yttrium, which Winston Chung used for a while. But any of the rare earth metals, molybdenum, vanadium, cobalt, manganese, to dope the array, the crystalline structure of the lithium iron phosphate so that it would carry current flow. That's scientifically kind of a dubious proposition. There's a woman who has done quite a bit of work refuting the A123 claim that that is how they achieved such high current. But they have achieved higher current densities on these cells than any of the other lithium iron phosphate cells. And so they have to have something going on there, and it can't be just carbon. But I can tell by feel that this cathode and cathode material is very different, and the carbon doesn't come off quite the same way. It's a much smaller particle. It's almost smooth and shiny here on the anode, where the cathode, the copper, which is carbon on copper, looks just like any other cell. And so that's kind of interesting. But there's a battle going on over patents, really. Here's the copper part. And you can see copper, and it just has graphite on it, really. And not a very good coating there at that. I'm kind of surprised the cathode, the anodes are not very well coated with carbon in this case. Here's another one that you can sure see an awful lot of copper in there when you ought to be seeing carbon on the anode. Same there. But the cathode is a shiny black material that is lithium iron phosphate, purportedly doped to be more conductive of electron flow, which of course is prevented by the separator. You have ionic flow within the battery. But once you're there and the ions are there, they should be attracted to electrons from the cathode, and you have to have that flow to have current flow. And the claim by A123 is, of course, that they get much higher power, and that's one of the reasons. Is this is a very thin coating of material, and it's a very fine particle, a nanophosphate powder, but that they have it doped for much higher conductivity. And so that's the heart of the A123 process. It's not working too well for me in my clumsy packaging effort here at a 80 amp hour, 40 volt module. And I had high hopes for this, and I still love this urethane resin. In fact, taking this apart, I like it even more. We have to pursue this and find one, with a temperature that the cells can survive to casting, because this makes them very tough. But if you over discharge or overcharge them to the point where they swell and vent, it's going to bust that resin. It will sure do it. The issue is to keep from doing that. I thought we were well on the way. We were zero balanced at 2.75 volts on all these cells, and we had measured them to 77.5 or 77.75 amp hours, and we never did take more than that out of them or put more than that in them, but somehow they lost capacity when they were cast. And then when we tested it as a module, it did not have 77 hours. In fact, it was more like 65, and kaboom. The first effort is here, and I think this one just suffered from spaghetti, but I hooked it up to our had a little lightning show. This one, the stuff didn't turn white all the way, and I got a little lightning show in here, and it still got 40 volts, but the internal resistance is so high, it goes to 0 volts immediately without any effort at all. And that is the other module, and it's just not doing very well. Its internal resistance is quite high, and the slightest drain and the voltage goes to 0. That was actually a function of something I'll show you next. This is kind of interesting. This is a GigaVac GX14BG high current relay or contactor, as you guys call them. I like these because they have these tabs with the things threaded. They're nice big terminals, and this will sit flat. It's a compact unit. I thought these might be a replacement for the Tyco Kilovac. As it turns out, there's a couple of problems. One, they're a little bit expensive, about 350 bucks a piece. Recall I said that HP EVS had told me that the Curtis controller required a 24-volt coil. Well, in my simple mind and my simple world, two 12-volt coils in series would be a 24-volt coil. And two contactors in series offers some advantages. If one of them, let's say, arced and welded the contact shut, the other one should be free to open at any time. And so two contactors in series would be very safe. I understand in Australia they have taken that as a, kind of a requirement for automobiles to have two contactors in series for that very reason. This didn't work a couple of ways. One, the two 12-volt coils did not add up to a 24-volt coil that the Curtis 1238 7501 controller would run. It just didn't work. And so we had to replace that with the ANA 5 level Tyco Kilovac with the 24-volt coil, and then magically it worked fine. I still don't entirely understand why that didn't work. Maybe somebody can explain it to me. This is one of the GigaVacs also taken apart, and the reason for that is we wanted to see what was inside. And there are some terminals there. Here are some terminals here, and that goes together like that, and that sits here, and then you of course have your screw terminals there, and so it's a little bit like this. Neat design. I like it. I think it's very elegant, except here's the horribly pitted, scarred copper contacts that were being used in this device. We had two of them in series, and this was roughly how I ran our battery test bench was I would turn the 12 volts to the contactors on, and they would close, and that would connect the battery to a load. And I had a series of them, two Acme 1500 watt loads, a Transistor Devices 3000 watt, and several others. Then I would turn off the little power supply that ran that, and that would disengage that and disconnect the battery from the load. And then on this side of the bench, I have an array of power supplies. One of them was a 100 volt power supply that would do about 100 amps. One of them is a 10 volt power supply, but it'll do 200 amps. And one was about 150 volt power supply and does 10 amps. Obviously, for a single cell, we like the 200 ampere 10 volt. But in the process, I did hook up a battery backwards at some point, and that set off a chain of events that we blew up a power supply, and then everything I touched burst into flames, blew a circuit breaker, melted AC power cords that shouldn't have even had anything to do with it, and it was as if the lab was possessed by demons. You just have to check the basics. What had happened was both of these contactors had welded themselves shut. Now, it's probable that one of them had failed at some point, and I hadn't noticed because the other one was still working, which is the problem with a backup system like this. When one element fails, if the other one's working, you don't notice the failure. And then the other one fails, and you've got both of them appearing to have failed at the same time. Probably didn't happen that way. But it sure did mess up my day while I'm running batteries, power supplies, and loads, very low resistance loads that can do a lot of power, but they can't do infinite power all at the same time. And I blew up loads, power supplies, obviously these, to the point where I was actually hesitant to come in the room. It seemed like if I would just step in here, circuit breakers would blow, test equipment would start showering sparks and go up in flames. Never mind what I've done to our batteries. But that's it's been a little harrowing. Mark Weisheimer, who works for Associated Press, I guess, as a satellite technician, had done some work here at EVCON to get us up wireless. And I sent him most of my test equipment, and he's working on it and has most of it repaired now. And thank you, Mark. That's very kind. So I'm hoping to have some of it. We've since got a load and are back up in business. And right now, let's go take a look at our latest cell effort and what we're doing here.
NetGain Controls introduces the new Warp Drive Industrial Controller. The Industrial is designed to handle a maximum of 1400 amps and up to a 360 volt nominal battery pack. The unit's rugged design looks and works great in the automotive environment while protecting it from the elements. In addition to higher continuous currents than the classic Warp Drive controller, the Industrial comes with several major enhancements. Liquid cooling is available and uses leak-free and rugged AN fittings. The Industrial controller has complete isolation on both throttle channels, giving the highest possible immunity from situations that might affect the electrical throttle input. High voltage connections are fully protected underneath the sealed cover. Voltage leaks between vehicle chassis and a battery pack are detected, alerting the user to potential safety problems. Controller settings can be completely customized using the NetGain Controls interface module, which can also log data to an onboard SD card. The controller weighs in at 25 pounds. Visit www.ngcontrols.com to order your Warp Drive Industrial Controller now.
We've suffered some failures in our module design. So if we can't do an advanced module, let's go back and do a simpler one and work our way up from there. The prismatic cells we get now I kind of like. This is not the keeper we use out of most of them, but I did get some very cheap cells, but they had a very good terminal system inside them. They were sort of Satan clones that I've had for a long time. Took a bad one and took it apart. This is actually a little block of steel that's threaded and has 2 holes in it, and a couple of plates, one on each side, that are held with simply a nut and a little cap bolt that holds these plates fast against this block. And so we can take that bolt right out. You can kind of see the plates. Now they're recessed a little bit. They have to grip these very fine foils, and so half of them go on one side of the block and half on the other. The bolts don't go through the foils at all. They go through the block and the 2 plates, and the foils line up between the 2 little nut and bolt pairs. Then there is a hole tapped in it, and this fairly elaborate terminal is then screwed in it. A bolt would normally secure your cabling to the top of this, and I've got one screwed in. It's a different and smaller thread, and then the larger thread, this screws down into the terminal piece and actually holds it to the top plastic of the battery. And there's a little hex side to this, and so it sits down into the battery. You tighten this down, and the plastic then is clamped, of the top of the battery is clamped to hold this in position this way, and the tabs of the foils go here and are clamped to all this with these 2 bolts. We can fashion something about like that for our A123 tabs. I've set my saw here for 2.4 inches, and that's going to give me enough length that I'll have room for a bolt hole in each side and still be able to get the tabs on. This is a piece of 1/4 by 3/4 inch aluminum stock. This is a piece of 1/2 by 3/4 inch aluminum stock. We're going to use the 1/2 by 3/4 to simulate our block here, and we'll tap into that with an M8 threaded hole for our terminal bolt, and then we will use these, 2 of them, one on each side, to clamp to the 1/2 by 3/4 to clamp our terminals in there. So I'm going to cut 2 of these and 1 of those for each terminal, and we're going to do 2 terminals for a battery. Take our 3/4 by 1/2. And there we go. And so here we have one, our big piece, and 2 of our side pieces. And now about all we need to do is drill a hole through them, and they're ready for a 1, 2, 3 tabs. Let's see if we can get a close-up of that. Over here on the drill press, we want to drill a couple of holes near the ends and the edge of our stock. I'm going to put it in this little vise. We're going to go pretty close to one corner here. It doesn't matter a whole lot exactly where. Now let's get it on the same place, on the narrow edge of our bigger stock piece there. Mark that one. And that one. Pull that out. That's got our holes drilled. Let's go clean them up on the buffer. With the buffer grinder, I can kind of take off the sharp edges. And more importantly, remove all the oxidation from the aluminum again, where we're going to get a good electrical contact. Deburr it nicely. That'll make us some nice shiny pieces that are deoxidized and conduct very nicely. What I've got for assembly here is two McMaster Car 8.5 or number 8 by 1.5 cap bolts. This is a our now familiar Nordlock washer, but for a number 8 and a screw. We're using 18/8 stainless again. These little bolts, and so this is going to make our little clamp assembly. Our tabs will go between the two bolts, and so we could put we're going to take 6 cells and put 3 on each side and clamp them together and drill us some holes and tap them in the top for our M8 bolt, and that should give us a pretty good pair of terminals to make essentially what's identical to our standard number 8 or standard prismatic cell of 120, probably 120 amp hours. So here's our Chinese version, made out of stainless steel. It looks like very nice machine thing. Here's the Jack's Machine Shop version, kind of ugly, aluminum, but I've got not much in it. A McMaster Carr 18/8 number 8 cap screw of 1.5 inches, 2 little number 8 Nordlock washers and nuts. We have 2 2.4 inch pieces of aluminum. That's 1/4 inch by 3/4 bar stock, 1/2 inch by 3/4 bar stock, 2.4 inches long. So I would, and a M8 bolt and a 50-cent Nordlock washer, probably less than $5 worth of materials in a few minutes time to make that. I think we could do those without too much trouble. 2 of them would hold our tabs. We could put 3 cells on each side and have a pretty good looking rig with that. That would certainly clamp those tabs strongly and put 6 of them in parallel. And we might be able to cast that in resin and see if that would work. Let's go test 6 cells and see what they look like. Okay, this is our 6-cell module, and you can see how thin 6 cells can be done this way. And we think that's about 3 kilograms or 6 pounds, maybe 6.5 with our hardware. And right now we're running some tests on it. The cells that we're getting seem to even be getting better. The deeper I get into the boxes, I don't know what, maybe we're getting better at dealing with them, I don't know. But on our first discharge, when we fully charged it and then discharged it at 0.5 C, really about 40 amperes, we got 114.93 amp hours to 2.75 volts, 117.91 amp hours to 2.5 volts, which I would normally count as the cutoff, and that's 19.65 amp hours, and that's right at spec for these cells. That's 19.65 amp hours per cell, and their spec is 19.6 amp hours, and that's at 2.5 volts. So I would call 2.5 volts the cutoff. At 2.30 volts, we had taken 119.62 amp hours out, and at 2 volts for the cell, we had removed 121.27 amp hours, and it probably over discharged it slightly, although they do call 2 volts the cutoff in their specification. From what I can see here, we'll continue to use 2.5 volts as the cutoff for these A123 cells on the low side, and on charging it, we got up to 3.65 volts at just about an amp hour shy of our 2 volt discharge, and we were right at 3.65 volts and had diminished to 6 amperes, which is 0.05, and that's the normal thunder sky variables we use, and they work very well for these A123s, and we're not going to charge them any higher than that. We're going to use 3.65 per cell, maybe even 3.5, and we're going to, in all cases, call 2.50 volts the cutoff. Right now, I'm recharging the cell to see if it retains this, and having some trouble here. Here we go. 1A point. We have put 68 amp hours back in it, so we're about half full. We're doing this at 46 amps at the moment. I mean to do that at 60 amps. 60 amps would be 0.05 C, and so we're going to see if we get 120 amps back in by 3.65 volts. Even though on this discharge we went down pretty close to 0 volts, about 0.1 volt on the cells, and we're going to see if that has any effect, or if that's any part of our problem with the other ones. We did not drive them into reversal because we have 6 in parallel. We can't, but we took them quite low and quite below the 2 volts, and now we're adding current back in at 0.5 C, 60 amperes into our 120 amp hour cell pack. And if that comes out to 120 amp hours again, or even close thereof, I think we've got a good cell here. And the next step, we're going to try our resin casting again, only this time in a 1 cell version, and then measure the discharge and recharge and see if that may be our problem. If it is, then our basic assembly of the module into 40 volts and our 12S 4P would still be manageable, but we can't cast it in resin. If this casts in resin and retains its capacity, then I'm going to say that I don't really want to fool with these cells in groups of 48 because it's just too expensive for the failures. We'll have to monitor the cells individually and treat them more like our regular prismatic cell. So that's short week this week. Brian's gone. I've shown you our modules. We've had some test equipment failures. As you can see, I'm in some disarray here, but we're recovering and able to do tests. So this is what we're working on right now is, again, these little clamps. Really, it's just, this is simple, cheap. It's not a big assembly process. It's not really a big machining process. I can run off a set of these in 20 or 30 minutes. And so we could probably have these made up and be able to do this quite easily, to make cells this way. We either have to come up with some sort of casing for them or this resin casting, and I'm still wanting the resin to work because it just makes them so tough. But we're going to continue to pursue the A123, but so far we're not having tremendous luck. Again, my packaging skills are just not, I'd like to get you guys more involved in it and me less involved in it and go from there, but right now that's what we've got to work with is me and some cells. I did sell Peter some 8 cells, I think, for 35 bucks a piece plus shipping, and I've got a few left around here if anybody wants to play. But I'm trying to find other sources. They are springing up from other places, and in quantities they claim they can do 6,000 cells a month. This one's 60,000 cells a month. I did talk to someone from a new company that I have not bought from before, General Electronic Battery Company of Shenzhen, China, and they swear that all 20 amp hour cells from A123 come from Korea, and that is where they derive, and that is where it's printed, made in USA, is right in Korea. And they can get me all I want, but they can't compete with the price that Shenzhen Vic Power has already delivered us some with. So we'll probably go back and do a reorder at some point. I've still got some left, but they're going quick on these modules. I've lost 96 on the first two 40 volt modules, and I am disappointed that that didn't work. It would have been a slick thing to have 3 modules be enough to run that Curtis 1238 at 225 pounds and just have 3 bricks to put in a car. But it didn't work out, and so now we're looking at making a little 120 amp hour cell like this, but that can do about 2,500 amps of power. And so that's the direction we're going next. But as always, if you have any other ideas of how to do a module, we'll be happy to look. I can show you one that we haven't talked about. We had made it, and I got off on this other one. A fellow named Kevin Wong, 17 years old, from Canada, showed me this. And it's just a little U-channel that we clamp the ends together and then put a little rod and a screw, and the screw forces the rod down and pinches the tabs between the things. It's kind of curious, but I'm not sure how long it would last or how firm our connection would be. This was an early version that was simply 6 cells clamped together with our normal little 1/4-inch bricks, and the plastics ain't meant to be, you know, put together, but I don't think we need to do all that for this. To put 6 cells together, these 2 sides in the top with a hole for our terminal and 2 little 1.5-inch cap screws, you know, this kind of strong stainless steel cap screws, seems to work just fine. So that's what we're going to go to for that kind of module. But you can see that we've been playing with different things. So that's pretty much our show for this week. Brian's out. We're charging the Escalade. We beefed up the cabling to the charger to 4 AUG inside the vehicle, put in our David Kurzel's AC31 module for the J1772, and we're charging the truck right now. We've zero balanced all the cells at about 2.75 volts each. They're 400 amp cells. I don't imagine it's too critical, but we're at about 2.75 volts, and then we're bringing the whole thing up, which even at 50 amps takes 7 or 8 hours of charging to fill a 400 amp battery pack, and that's what we're doing at the moment. And I'm playing with the A123 cells and trying to get a little show put together for you for this week. For EVTV, I'm Jack Rickard, and we'll see you all next time. I'm Jack Rickard with just a quick reminder that we are now in the braided copper strap business. Here's 2 China Aviation Lithium Battery Company 100 amp hour cells and one of their 180s. All of these you have essentially the terminals on 70 millimeter centers. In other words, if you put these 2 cells together, they'll be 70 millimeters apart. Here's what they send you, is a little copper strap that has about 4 or 5 laminations, 3 or 4 laminations of copper and a little bit of heat shrink. And you put that on top of the cell with a bolt and a lock washer and a washer. And you tighten that down onto the terminal. And that works pretty well, looks pretty good. The copper does develop some corrosion over time, just gets kind of nasty looking. But worse, these bolts gradually work their way out. They back out from the vibration going down the road, and from the thermal cycling of running current through this strap every time you accelerate, and cooling when you decelerate. We've come up with a system I like very well. These are 50 square millimeters of braided copper that is tinned and enclosed on the ends in kind of a sheathing to make a hard end out of it. And they lie much flatter on the cells. And as the cells move, it's more taken up in that braid, which can twist and flex much easier than the little bent things. And so we don't pry on the terminals. We use essentially the same bolt, but we use a Nordlock M8 washer. The Nordlock wedge lock washer bites into both the bolt and the tinned copper braided strap. And when we tighten those down, they bite in, and they simply do not back off. We have eliminated pretty much with this the problem of cells just magically working themselves loose. I tighten them, I don't torque them, just use a little stubby 3/8 inch driver and a 1/2 inch deep well, and I wrap that in electrical tape when I'm running the batteries, and I just give them a good twist. That makes a very positive connection. I can come back 6 months later, that connection will be just as good as it is now. We use an inexpensive little 3M sanding block from Lowe's to remove any corrosion from the terminals prior to putting these on. And so that's our best solution we've been able to come up with for how to interconnect these cells with the lowest profile, the lowest level of corrosion, and to maintain these connections even on those cells that are hard to get to and difficult to inspect. We have to be able to rely that connection is going to remain clean and tight as we use the car. You can order that from our online store on at www.evtv.me at $7 a set for 2 bolts, 2 Nordlock washers, and 1 tinned copper braided strap in any quantity you like, plus shipping. And for most of the EV size orders, we've done 55 to 75 straps. It's been between $20 and $25 shipping is what it'll come out. UPS ground, you know. So order today and help us get rid of our 1 Brazilian 70 millimeter straps. We also offer 60 millimeter straps that work with Thunder Sky 90 and some of the Thunder Sky 100 amp cells. The larger Thunder Sky shells use these 70 millimeter on center straps. So this makes a very flat connection. It doesn't corrode for a couple reasons. One, the strap is tinned, and the tinning is between the copper and the aluminum in your list of active or noble metals. And the lowest on the list is zinc, and our Nordlock washer is zinc coated. And so if anything in this pile of dissimilar metals is going to corrode because of galvanic action, it will be the sacrificial anode of the zinc washer, and not your strap, and not your terminals, and not your stainless bolt. And so That's why we get the zinc-coated Nord-Lock straps, washers. But those Nord-Lock wedge lock washers really do keep those connections clean and tight. We do not use thermal grease. We do not use nail locks. We do not use any of these liquid cream magic things. I like to see the connections, see they're clean and tight, and make sure that none of the cells are venting or anything. I like the connections to be clean, dry, and tight. And but it is important that they be maintained. And some battery packs, it's difficult to get to all the cells, and so we have to make sure they have a good connection when we install them. And I would urge you to do the same. Anyway, I think we're in the braided copper strap business because I had to order a Brazilian of them to get mine for the Escalade. And so our joy is your joy. If you want to share, it's $7 a set, and it takes a strap, for each cell. And that'll give you the best way of interconnecting the prismatic cells that we've found so far.